You're going to get the answer completely wrong. On the test, we're trying to make this design work. I was working for a London-based company over in London, and we were doing design for reinforcing of some bridges for a Saudi prince in Saudi Arabia. And our engineers were overloading the reinforcing because they were getting paid on the cost, a proportion of the cost of the job back in the 1980s. So in some ways they were ripping off the prince at the time. And then an Egyptian engineer did some calculations and came back and said that we were doing it wrong. And immediately our company fine-tuned everything so that the reinforcing was exactly as all that was needed. They just thought because he was wealthy he wouldn't care, he'd just keep throwing money out the door. But you'll find that in most cases in New Zealand they design as close as they can without wasting money. I guess that's just the way Kiwis are. So in that case they would say, no, it still works with 90, do 90, don't put another bolt in there. Incidentally, when you come to detailing up your plate, and a lot of you are going to forget this, but I'm saying it now, I will need the size of the bolt, the size of the bolt hole, the distances between the bolt holes, and of course anything that's welded to that plate will have to be shown in plan view as well. And the overall dimensions of the plate. So it's quite a tricky little detail to draw up. I do not want the detail on another sheet. That's basically cheating. That's doing another viewport with a picture of a plate on it. I want it to be referenced to the drawing that it comes off. So if it's a plan view, you'll need little flags looking down on it, won't you? If it's a detailed view where you can see it sideways, then you'll need a circle with a bigger circle over here with the detail inside it. Have a look at some of those examples that I pointed out in the notes. The famous girder. So some examples of what I have mucked around with. Okay. I've mucked around with that in the test. I've mucked around with that. So they'll be different members. I've mucked around with the plate size. So that'll be different. I've mucked around with the angle. So that'll be different. And I've mucked around with the overall length in metres of the beam. If I've used a different angle, then that 14 kilograms per metre will have changed as well. And so really it's kind of applying, this is probably a lot easier than a lot of them, you're applying the mathematics of this to a very, very similar example. The sketch will look exactly like that. So I'm not holding anything back. Incidentally, on the assignment, you were told to use the kilograms per metre that was used in this. You were told to use 7850 as the kilograms per metre. You weren't given the 14 kilograms per metre for the angle, so you had to work it out. The easiest way to work that out was to look at the cross-sectional area of the angle that I gave you on the plan, on the AutoCAD drawing, and to also on the AutoCAD drawing was the length of the angle, whether it was 50 or 100 or whatever. So you actually ended up being able to work out a cross-sectional area, which is the volume, and if you multiplied it by the volume of steel, you came up with an answer for each one of that. There were 3 angles, and yes, you would have needed another column for the volume to work that out. So you needed at least another one column on this schedule. Okay, so here's the schedule here, and that's kind of exactly the way things are going to appear on the test. So you'll get a sketch. Be very careful, it won't equal the exact numbers on this. You'll get a schedule like that with the members called up, and you'll get missing A, B, C, D, Z, F. Now, English second language students, you don't have to do everything. You will be asked for A or G or D or H or P. Hopefully you won't get asked for N. Okay? That would be the one where you start going, oh, I think Roger's picking on me. Because for N you'll have to calculate everything. So, all going well, you'll get asked for one, and then another one of these will appear. Once again, be careful to check with the second one that all the numbers, you know, they're not the same each time. It might say figure 1 or figure Z or something, but that's just me mucking with you, because what students do is they see their friends got figure Z and they're like this, like as if you're on the motorway and you're looking at an accident. You'll find the numbers, even though they're the same figure number, they've actually changed. So I've spent a lot of time making these tests up with different numbers and different answers. And you can be assured they're being checked right through to the very end. So how do we work out this again? Just going over it so that, because I know a lot of you are very unclear on how this works. Looking at the beam first, all right? And a lot of people couldn't work out that a beam is very similar to a column. When we call it up, see how it's called up as a 533 UB 122? The 122 is always the weight per metre. And it's the same with the TFC. The 46 bit is always the weight per metre. So if that said 42, it would be 42 kilograms per metre. If that said, instead of 122, it said 105, it would be 105 kilograms per metre. And that's extremely important when you're working out both of those numbers. Now, I keep telling students, look, your column on your assignment is very similar. And they're like, no, it's not. The column's like that, and this is like that. They couldn't see that it's the same type of thing, but in that direction. So all you needed to do was measure that length, and you nailed it for the assignment, right? So in this case, we need to know the length in that direction, and it's 12 metres. So the length down the bottom here for both of these two, A and D, is 12 metres. Now that's an easy question. You got that in the assignment, like, okay? So what I've done is I've gone through and gone, well, John Smith, he's going to get an easy one and two hard ones. And Jane Jones, she's going to get an easy one and two hard ones, all right? And I have had students come back and said that Moodle didn't quite do it right, they got two easy ones, but it's my interpretation of easy. Looking at the number off here, that is also easy, B and C. B, there's only one. So all we had to do to get that answer right will be 1. C, there's 2 at this end, and there's 2 at the other end. Okay? So that would be 4. Plate, there's 2 of them, 1 at each end. When it comes to the angles, E is the hardest one to calculate, so I'll do E for you on the board. And the mass per metre, G, H and P. Now in my opinion, that is harder than doing the others, but a lot of students think that's easy. To me it is easy. G will equal 46, H will equal 122, And P, the mass per metre, in actual fact, that is given up the top here at 14. And you will be given it in the assignment, in the test. So just remember I said I would calculate, what did I say? I'd calculate the length here, E. So I'm going to do E on the board. And the total weight, I'll also do the total weight for the plate on the board as well. So E, how do we calculate E? Just refreshing your mind again, the beam sits here like this, and the angle fits in here. So that length there is the important length that we need to calculate, and we can't do that without knowing what the overall length is. Our overall length is this one here, 533, 21.3 equals, you want to know the answer to that? 490.04, isn't it? I'll just check that. It's 490.04. .4, sorry. But if you put that in the answer, you'll get it wrong. Because if you have a look at this table, everything is in meters. It's not actually obvious. Oh, there it is, 0.5. So the answer that goes in there is 0.4904. A meter will accept 490 as well, or 49, because, but you need, if you want to get it perfectly right, I'd put 4904. I think I've made that one so it will accept slightly wrong answers. But 4904 is the best one to put in here, this one here.
So how did you know that was 21.3? How did you know it was the big thing or the little
Up
thing?
the top,
Yeah, but how did you know if it was the big thing or the little thing?
the little T on a beam, if you can have a look at the sketch, the bottom part is always the fatter part, or the web, versus the flange. So the thinner part on a beam is always this bit here.
So that's the little thing.
That's the little T here. When I started teaching this some 15 years ago, Play School was still big on TV. Everybody remembered it for some reason. Play School used to have a big T and a little T. And I used to tell students that is the correlation. Everyone's still looking at me blankly. It's all right. Wonderful thing growing old, no one knows what you're talking about. Okay, so let's look at this calculation. Here's another one that students often get wrong. This will normally be put in here for you. The length is always the first one on the quarter. The next one is 250. So this one here will be 250. That's, in this example, that's the weight of steel. And then you multiply it by the thickness. That's an easy mistake to make. It's 0.02 is 20 millimetres. So everything's in metres. And so what you do is you multiply that by that, by that, by that, and you end up with an answer L. So I have actually got that answer here, which will be made available for you afterwards. Just far as that goes, there's also a worked example on Moodle. We'll need to work the way through. Is there any questions about that? There's a few things there that you have to get your head around. Now for the assignment, most of you would have used this table, maybe added a column or two. Had a lot of students saying to me, oh, it doesn't work for your example. Well, that example was a completely different drawing, and it was just an example of how to lay out the sheet that I was after. You also would have found that the nuts and bolts didn't work either because there was quite a variety of them. I expected you to call them up by their length. If you had a look at some of those sketches, you would have seen that the length is actually from that point there, and whatever material you're going through, you would allow a very minimum of the nut, which is the diameter of the bolt. That is the diameter of the bolt, and at least a diameter of bolt of 3. So overall, the length of the bolt is taken from that point to there, which is logical when you think about it, because that's how much material that you want to go through, plus allowing for the nut to go on, plus approximately another nut as well as a attachment after that. Now there are exceptions to that. You may not want that bit sticking out, it might jag on something, but generally speaking you can chop those things off. And the other exception, if this here is wood, then you also need a washer, which should have been called up as well. Okay? The washer in that point there, that's generally 5 to 6 mils. So when you guys call up a distance for the length of the bolt, that's my calculation. If you're close to it or roundabout, I'm fine with that. But if it's too small or way too big, or you didn't put it in at all, then that's a critical thing missing. As far as what else was there? The types of bolts. There was the lag screws as well, and whether they needed washers on each end or no washers at all. The lag screws would have been stopped by the angle, so they wouldn't have needed a bolt, a washer, and the lag screw goes into the wood, so that it didn't need a washer on that side. So you needed to think about those things. The Dynabolt, if you look at a picture of that on Google, that goes into the concrete, and it has its own washer attached to it, so it doesn't need a washer either. So that was the sort of thing I was expecting you guys to do for the schedule, as well as schedule everything else. I'm not saying that was worth millions of marks, but I am saying that it's part of the schedule, all right? This steel was worth the most in terms of the quantities, because it was the hardest to do, in my opinion, including the bolts for the steel. Timber was, you needed to say whether it was, either you needed to say it was tantalised, or you needed to call up a number like H3.1 or something like that. It needed to be the dimensions, which could have been, I don't know, 100 by 50 or whatever. And you needed how many of them there were. So if it was the purlins, overall length, and how many there were on there as well. If it was the rafters, the dimension for the rafters was tricky. Came down like that, right? And then up to a point up like that. Well, that is the dimension you should have used, because if you used anything less than that, then they wouldn't have been able to get it out of a piece of timber. So that's what we call wastage. I don't think there's any chippies here, but I've had a lot of carpenters and chippies and that have done this course, and normally there's a 10% wastage allowance. Not on anything I do though. If I go down there, I'll spend 3 hours at the timber yard trying to make it exact, but chippies basically get it delivered to site. And so they would also probably add a little bit of length onto that, so that when they went to cut it, they didn't end up with a situation that was too small. So I was a wee bit flexible when marking that, as long as the length wasn't too small. The hardest part with the concrete calcs were you needed to have a quick look at my updated little sketch, because it showed the first one had the ground slightly wrong and didn't have any dimensions. The updated one I loaded there on Thursday last week had the dimensions so you could calculate the earthworks. The earthworks were something like that. Also had to be taken into account the hard fill underneath. So here's where the ground line went. So the earthworks you had to take into account was that. Oh, sorry. So that was your earthworks part of it. Obviously, including that was, you had to work out how much you would scrape all the way along, including these pile holes. I would have done it by doing that calculation first for that bit, because that goes all the way along, and then I'd have done each pile separately. All right, I'll show you the answer to those at the end. What I need to do now is talk about this, and then we can run a break. Right. So, what is an abutment? An abutment is something that looks like this. And there's usually another one over here. And what happens is we put a bridge pile goes between the two abutments. Now the abutment may be set sort of in the existing ground line, like this, or a riverbed or something. And often we have like a pile with pole caps, the pole cap being that bit there. We might have some raking poles going into the ground, and this could be holding up a beam either side. These beams could be precast concrete, and they sit in that slot there, and often we have another beam leading into what is the existing road. So when you're driving along in the car, you're going to hit that first piece of concrete and you feel the wheels just go hook. Then there'll be this piece here which will make a bigger bang, because normally we fill up this bit here with a expandable material, kind of a little bit like rubber, so that when the concrete expands and contracts, and also underneath here we have an absorption material as well. So the car will go bang bang, and then bang bang with these two joints, and then bang bang as you come off the bridge. Some cars, if you're lucky enough to own a modern car, probably don't make quite as bad as maybe a student car might make. You can write that down on your review. Thinks that we all drive rubbish cars. Okay, so that's what a pier looks like. And you'll see a good example of this over in Newmarket perhaps. you some examples over on this construction job here, but the big bridge at Newmarket, when you come into Newmarket, you turn off the motorway and you go down, you'll see that underneath there the piers where it's sitting, or the start of the bridge. So breaking it back, we're going to do a reinforced concrete drawing for this shape here. Now when we refer to the width of an abutment, it's not that distance there, it's this width here. Think of it as how wide is the road, right? How wide is the bridge? So there, you'll notice that I've, down the very bottom, number 4, I've put width of abutment. Now that width is not 1550, it says 3.7. A lot of students get quite confused by that. That is not the width, that is the width that way. So that having been explained, we have to do a reinforcing drawing. Now, one thing that I need to be very, very specific about is how these bars work. This is your one and only chance to look at this. And this is what you guys do, and I know you do it, because everybody makes snapshots. You go like this. Oh, Roger, it looks like these two bars, one's outside the other and the other one bends, and it bends halfway on this thing here, and drawing it from, This is a sketch. And the reason why I do a sketch is because you're going to get a sketch in the office. You're not going to get a beautiful engineer's drawing to draw this up. You're going to get someone that's got out a pen and a piece of paper and a pencil, and he or she has sketched the design. Right? So please don't take this on the face value of what it looks like. And I see students in the test going, I can't work out what bar is what. Which one, is that a lap? What's happening there? Remember the plate? You push it as far out to the edge as possible. It's exactly the same with this. Absolutely no difference at all. You've got a bar that goes up and bends like that. Please, those students that don't take photos of things, if you're going to not take a photo of anything, don't not take a photo of this. Alright? Because this will help you very much in the test. Now the principle of this is exactly the same as the principle of the one I went over in class. Remember we did a retaining wall like that? Of course you do. We did that as an example in our lab, and I went through the mechanics of working all out. The only difference is these bars are different. So this one here, for example, goes up here. And up like that. I know it's a rough sketch, but you can see there that the bars are pushed right up against the cover, all the way around. Probably that's a little bit of an exaggeration, it's probably more like that. And yeah, that's how it is. And the bars here start here, which is exactly as per the example that we had. And up the top there, now the expansion, so the joint will be there. So we have to assume that this is going to be poured in 2 pours. you can see that that bar comes down. This one here comes down and touches. So 1601, which is the bar there on the left, and 1602 is the bar on the right. To calculate 1601 and 1602, we do the following calculations. So it's a red bars. Is it O2 on the right? O2 on the right there, and O1 there. Calculate them. We have the distance, and in this case it's 1,000. 1,000 minus the cover at the top. CVR. So this bar will rest directly in line with that point there, which equals 900. And now where's the cover? The cover's given to us. The cover is 40 minus 40. So it's 960. So therefore we can put the first two numbers down for the length of the bars, number 1601 and 1602, G and H up the top. 1603 and 1604. Okay, this sketch is really important, and it's going to rub against the grain for some of you. You can argue it if you want to, like a lot of students have for the last at least 10 years. But at the end of the day, my answer is the one that's in Moodle. So you either do it my way, or you can argue about it and create a stand if you want to. It's not what you think. So this bar here and this bar here, let's do this one as an example. We're talking about 1603. So 1603, in order to calculate that, it goes like this. And what we do is we calculate A, B, and C.